Good afternoon, everyone, and welcome to today's Quantum Leadership Session hosted by the Quantum Business Network. My name is Mila Kurunovska. I'm the Marketing and Event Manager at QBN, and I have the pleasure of moderating this insightful session featuring such a strong lineup of distinguished speakers today. In today's session, we'll explore how cryogenics and control electronics support the advancement of quantum technologies. These key areas basically help improve stability, accuracy, and scalability, driving progress in a range of quantum applications, really. So today we are joined by 5 outstanding QBN members, starting with Claudius Rieck, who is the Managing Director at Zurich Instruments, Germany, and he will discuss the topic of accelerating the second quantum revolution. Then we have Dr. Artem Nikitin. He is the head of sales at Delft Circuits, who will discuss the possible route to scalable quantum computer. Next, we have Clemens Schäfermeier, who is the principal scientist at Atocube Systems, and he will share his insights on cryogenics becoming a commodity. We then have Jan Spalek, who is the co-founder and CTO at Qtra, and who will discuss the cryogenics from last characterization to large-scale operation of quantum circuits. And last but not least, we have Yigit-chan Uzun, who is the quantum application scientist at Qblocks, who will conclude the session with a presentation on the fully integrated quantum control stack. So today, our esteemed speakers will share their insights on the role of control electronics and cryogenics in quantum technologies, highlighting key developments, challenges, and their impact on the future of the field. So these quantum leadership sessions serve as a platform for thought leaders and experts in the quantum space to discuss latest advancements, share insights, and drive innovation in the industry. And to really stay updated on future sessions and watch previous discussions, we encourage you to subscribe to our YouTube channel, which is QBN, so Quantum Business Network. Let's quickly go over the agenda for today's session. So I will start with a brief QBN introduction and an overall overview of the Quantum Business Network, which will be done by me. And we'll then hear from our esteemed panel of speakers who will share their insights and solutions on the topic of control electronics and cryogenics. And after every talk, we will open the floor for a brief Q&A session where we encourage you to submit really your questions or comments, either through Zoom or YouTube, as the session is being live streamed on YouTube. So please feel free to engage with us throughout the session, and we'll be sure to address as many questions as we can. Moving to the next slide, I would like to just briefly talk about our upcoming quantum leadership sessions. These sessions are really designed to bring together, again, as briefly mentioned before, thought leaders and experts in the quantum space to discuss cutting-edge topics and the latest advancement in quantum technologies. So we warmly encourage you to visit our website where you can register for the listed on this slide here, future sessions, and really stay informed about all the upcoming events. And then I can start by outlining a brief overview of QBN and what we do. So basically, QBN is Europe's leading organization in the quantum industry, working at the forefront of quantum technology development. As a one-stop shop for quantum vendors, facilitators, and end users, QBN provides access to a dynamic international network, strategic partnerships, and really tailored business opportunities. Our mission is to basically accelerate innovation, commercialization, and industry adoption of quantum technologies by bringing together key players across the entire value chain. So through events like this and today's session in particular, we aim to foster collaboration, share knowledge, and support the rapid growth of the quantum industry. To this purpose, QBN has an extensive package of services, and they are built around 2 key pillars: Global Innovation Network and Business and Innovation Services. So let me just quickly give you an example from each. Global Innovation Network, through our, let's say, matchmaking services, we connect companies with the right partners to foster collaboration and drive innovation across the quantum value chain. And for example, in terms of business and innovation services, we offer strategy workshops to help organizations unlock unlock their business potential, navigate challenges, and scale efficiently and effectively within the quantum ecosystem. So these are just a few examples. As you may see from this slide, we have many more services to offer, but to learn more about how your organization can benefit from our network and really join our mission, I strongly encourage you to visit our website, where you'll be able to find more details about how we can support your growth and success in the quantum industry. This brings me to the next slide, which is membership and community. So basically, QBN is an international network open to corporations, research institutions, and organizations working in quantum technologies and its value chains. Being part of QBN also means really gaining access to a global ecosystem of industry leaders, researchers, investors, and end users, all working together to drive commercialization and adoption. And as you can see, we have more than 100 members. Basically, over the past years, QBN has grown quite rapidly, now currently counting more than 100 members across various industries. So from component suppliers to full stack quantum technology providers. The idea is that our members really collaborate to solve industry challenges, explore new business models, and accelerate the path from research to market-ready quantum solutions. So really, by joining QBN, companies can gain direct access to a powerful network of experts and decision makers, helping them to stay ahead in the fast-moving quantum landscape. So once again, you're welcome to visit the website to really get some more information about that. Then moving to the next slide, I would just like to highlight that QBN success isn't just in the numbers and in events, but it's really in the impact we create together. So just a quick overview, we have facilitated over 200 million in private and public funding. We have established 4 task forces and 5 technical working groups, driving really key industry discussions. And we have held global events, conferences, and strategic partnership, expanding our reach to over 20,000 industry professionals worldwide. So our influence really extends beyond the industry. We actively engage with governments and policymakers to really ensure a supportive landscape for quantum innovation and development. And at QBN, we constantly really work towards moving the quantum industry together. And again, the key to this really lies in the strength of our collaborations. So without further ado, I would invite you to join QBN and become part of this global movement towards a sustainable and resilient quantum economy. I would also invite you to stay connected with us by following us on LinkedIn and YouTube, and to stay also up to date on quantum job openings, industry news, and events. And of course, to really subscribe to our YouTube channel for exclusive content like these sessions, for example, webinars and additional expert discussions. Lastly, if you're ready to take the next step, sign up on the QBN portal to become part of this really transformative network. So with that rather brief introduction of QBN, I would like to now turn to our speakers, who will share their insights on the role of control electronics and cryogenics, as mentioned earlier, in advancing quantum technologies. So our first speaker for today's session is Claudius Rieck from Zurich Instruments, Germany, who will begin his talk on accelerating the second quantum revolution. So Claudius, you're welcome to share your screen.
Thanks a lot, Ludmila, for the introduction. I hope you can understand me correctly, and I hope you can see my presentation as well. So today I will talk about accelerating the second quantum revolution. Now, what does that mean? For us, this is pretty instrumental because this is nothing short than Zurich Instruments' quantum mission. Our mission is accelerate the second quantum revolution and help build useful quantum computers. Now, let's add a little bit more context to that, yeah? So what does the second quantum revolution actually mean? So what is new? If we think about the first quantum technology or quantum revolution, we can think about things like chip design, smartphones, nuclear energy, but also MRI scans, etc. All those technologies were enabled by understanding quantum technology very precise. Now, what is new in the second quantum revolution is actually that we are not only observing quantum phenomena, but we start manipulating, tweaking them. We can take, for example, quantum communication, where we entangle photon pairs, for example, to secure our communication channel. The same way we can prepare quantum systems to act as super sensitive sensors in the quantum sensing or quantum metrology part, or this is a main element I will talk about, is quantum computing. So where we put quantum systems into well-defined state, entangle them, and use them therefore for different computation. As Zurich Instruments, we engage in the end, in all of those elements. On one hand side, we have our outstanding lock-in amplifiers with which the entire company start and which are used in many quantum sensing applications and also in characterization for them. But the main part I will talk about today is our engagement as in the control electronics for quantum computers especially. So let's dive into that and ask us the question, why is quantum computing so relevant? Why is there this huge amount of money also put in? And the answer is pretty simple. If you look at this graph here, you can see the ability of classical computing increasing more or less linear. You add capabilities and there is still some opportunity space above it. Quantum computing is supposed to have a super polymorphic advantage, maybe even exponential at some point. And this is the opportunity we are looking at. Now, but we also need to be clear and honest about the actual capabilities. Today, we are not there. We are potentially in this phase of being quantum ready. And also here, to get a little bit more details on what are the potential applications. Why is this bus so big? And on the you can see on the very upper right-hand side, we depicted a summary of typical use cases which are foreseen. We have to be clear; those use cases are on logical qubits, which you can which are depicted in a logarithmic scale on a left-hand side. So at the moment, we are basically here, we have individual logical qubits, and we need thousands of them, or at least hundreds of them to go in this regime. Also, the circuit size will need to increase a lot. And so the first thing which might be possible is in the direction of quantum physics, simulating correlated systems, etc., which might be a first use case with the least resources. Also, then going towards quantum chemistry, simulating big molecules. And then, of course, this is where the big hope is going for cryptography, optimization, where you think about logistic problems, box packaging problems. So in general, optimization problems. Now, the main question is, what do we need to go there? And this is exactly why we are here today, right? What we need is, I mentioned already, 10 to the 5, 10 to the 6 physical qubits, so going in the direction of 100 to 1,000 logical qubits. And this is what you see here in a nice picture of Google. They envision it like a not only room, but building size quantum computer where you can then do real fault-tolerant, error-corrected quantum computing. And at the moment, we are more here on the left-hand side with individual logical qubits. And the main message, and I think this fits very well to this session, is there is a lot of technology which needs to be developed to go all the way from where we are today to where we need to be in the future. And this is exactly where the enabling technologies play a major role, because it's the QPU design, the quantum chips is one element, but there are much more. And to scale those quantum computers, in the end, we have to think about two elements mainly. So on one hand side, we want to still work on better qubits. So this is still the research part going on, right? We want to, for example, improve qubit architecture. We want to optimize the operation and so on. This can be done in fairly small qubit bunches. And there is a lot of research needed. In addition, we have the track of scaling QPUs. So there we want to think about possibilities about quantum error correction. We need real-time decision-making, for example. And we need, of course, many channels, not only a few tens, but really thinking towards the thousands, the 10,000s of channels to control qubit. And in the end, to be honest, this is also pretty independent of the technology. No matter if you use superconducting qubits, you can also think about semiconducting spin qubits, neutral atoms, and so on. If you want to have 100,000 or million of physical qubits, you have the need for all these enabling technologies. And a way to go there, where we are realistic today, is what you see on the lower right-hand side. Is a chip from ETH Zurich, published in 2022. Our friends from the Wildorf lab demonstrated first surface code there on superconducting qubits. And you see that this went towards what Google released late last year on the Willow chip, where they showed to decrease the error part continuously. Now, going back again to the quantum computing setup in general. So this serves actually very nice for what we're doing here, right? In the very center, you see two different quantum computers. They typically have a quantum chip. So this is the quantum device where the qubits actually live. And then you need many things around it. On one hand side, I call it the infrastructure. This is, I'm sure, what Jan will talk later about. And also our friends from Delft circuits. So this is how you get signals to the qubits and how you calculate, set up the infrastructure. You have the software part, and you need, of course, the control and the readout part. And this is where we are involved. So if you think about the quantum stack, we connect in the end the quantum world at the very bottom with the quantum device to the classical world where the application on the application software application layer is sitting. I will not go in too much detail how this looks like. In the end, simply put, we have on the left-hand side our software where you program the quantum computer, the electronics in the very center, translating this into control signals. And then on the right-hand side, we have the quantum processor, again, with the example of the Wildorf lab. Now, thinking into the next direction about what do we need to get practical quantum computing. So we identify in the end three key challenges towards fault tolerance. The first one is quantum error correction. We already talked about it. So here is really about breaking the limits of the computational depth and being able to control qubits and reduce the errors. Then we have scalability. So we really need to think about a co-design, not only of the QPU, but of the entire quantum stack, from the hardware, connecting the quantum devices to the higher levels, but also to the software. And it is not only the stack, it is also our organization we need to build around. Very crucial to get to real scalability in this topic. And as a last step, this is the fidelity. We need to reduce the overhead to some practical sizes. So we need to be able to, for example, control fidelities very well. And we need to be able to operate individual qubits, but also big number of qubits on a QPU at the perfect level. I will have a few success stories on exactly those, how we do that. And as the first one, I would like to show high fidelity gates with our SHF Plus series. This is our latest hardware. We improved the analog front end, so you have outstanding noise performance on amplitude and phase noise. And this allows the Nakamura group in Japan to perform record-breaking gate fidelities of CSAT gates of 99.92%. And there was machine learning as a very crucial element involved to optimize the pulse properties of controlling those signals using towards the double transmon coupler, which allowed in the end to keep those high fidelities also during operation and using the fast data exchange between the control electronics and the host computer. This becomes also very important thinking towards connecting to HPC centers. With that, we move to the next one, because how do you calibrate a QPU? We have here a small 5-qubit chip. We did this work together with our partners at WMI in the part of Munich QC. So they are right next door, very locally. That's great. To work together, we have a 5-qubit chip. We only tuned up 4 qubits, which were accessible at the time. This is only small details. Now, we have a acyclic directed acyclic graph, which we step through for all individual qubits. And in the end, they turn from uncalibrated to having them calibrated completely within, at the moment, we achieve something like 5 minutes, and we're pushing this further to improve it better. So I called already discussion this morning, and I was told, yeah, now we can do 5 minutes, but I didn't want to claim this yet. So maybe something for the APS meeting next week. Let's see. Now on fidelities, so to summarize what we have there, we need the right technology. Yeah, I already told you about the outstanding noise performance which our analog front has, and we keep this. In addition, we need automated tune-up and recalibration routines to keep the high fidelities of our qubits and operate them at the perfect operation point. And all of that we put together in our new applications library, which is part of our Lab1Q software, which allows you as a customer in the end, and a user to have a very flexible and intuitive software setup to control your qubits. With this, we go to the next point, the scalability. Now, what we need for scalability is the scalable system. Let's not talk in too much detail about it, because I think we all discussed the scalable system so far. There is something else. We have operational excellence. What does that mean? Operational excellence, I hope you can see the video where we fly actually through our production. We need to be able to manufacture our instruments on an industrial level. We are manufacturing industrial components, which allows them to run 24/7. It needs to be scalable. Again, we want to achieve thousands and hundreds of thousands of channels. So also we need to be able to have the production and the manufacturing very well under control. And also, of course, quality and risk management. It is a nightmare if you want to operate a quantum computer and, for example, your supply chain is not stable. We need to be able to have very short turnaround times also when there is, for example, outage, when there is accident at one of the computing centers and we need to put in new instruments fast, and therefore we can rely on our outstanding technical and application support and use our reliability as a stable company. And this is where we actually benefit from being part of the Rode and Schwarz group. So at the same time, we are independent and very agile and still have access to the technologies which are in the operations of a big corporate, which allows us to focus on long-term success. With that, I would like to come to the third part, which is quantum error correction. So here I brought a success story of adaptive control. Our friends at ETH Zurich and the Waldorf Group published this actually mid last year. They demonstrated the realization of a fan out with real-time feed forward. They achieved feed forward, including recovery pulses below 1 microsecond. All of that was running on a 17 qubit chip. And we were able to demonstrate this for the first time, that you have a constant depth in real-time feedback, which is very crucial if you think about scaling and also stacking real-time error correction capabilities and if you want to go significantly beyond 100 qubits and more. This is all already built in. So with that, I come back to our 3 building blocks for scaling quantum computers. The first one is the fidelity. The second one is scalability, where we have a proven system. And the last one is the real-time processing, which is allowed by the architecture we choose in place. And we have a constant latency over the entire setup. And what we deliver is we deliver the right know-how. See here 2 experts from ETH. One is now our colleague, Sebastian. We can really communicate on eye level and support you directly in the lab, be it in academia for top-notch research or in industry. We provide the right architecture for your scaling, and we provide the right tool set with not only the hardware, but also our software. And with that, so our strength, I already told you, for you as our partner. This means in the end, you have 200 additional colleagues who support you. For academia, you can focus on cutting edge research and really come out with the next best paper. Curious to see that. And for companies, this helps you to reduce risk and of course, reduce your time to market to be really quick and get an edge in the quantum race. So I'm very curious to hear what are your plans. So feel free to reach out and discuss with us. And with this, back to you, Ludmila.
Thank you very much for this insightful presentation. Now I would like to open the floor for questions. Please feel free to ask your questions in the Zoom chat or in the YouTube comment section, and we'll make sure to read them for our panel to address. Let me quickly share my screen showing the agenda once again. I see no questions in the Zoom chat. Does anyone here have any questions?
Maybe I can ask a question.
Sure.
Hi. Claudius, what's your vision on miniaturization of room temperature control stack? Because it seems like your stack is growing quite seriously with the growing number of qubits. Are you planning to miniaturize the boxes components?
I think the answer is kind of obvious, isn't it? I mean, although we might have rooms full of electronics, still you need to miniaturize. You need to think about more highly integrated solutions, and of course, you have to think about that along the entire stack. And I'm sure we can have there a lot of interesting discussions also in the combination of the connectivity, miniaturizing that, and combining it with also more highly integrated electronics, the need is not only the pure volume, it is mainly cost. So reducing cost and going to maybe a few hundred of US dollars per qubit, thinking a few years ahead. And it's also about power consumption. Because if you have individual FPGA per qubit, so to say, this becomes very costly, and also your power consumption will not be manageable. So yes, absolutely, this is a crucial step for our future generations.
Thank you. There is also one question on the YouTube comment section. So when the error correct quantum computer will be available?
Oh, that's one of the most famous questions. I think at the moment it would be not wise to make a hard statement. I think we can all be sure that a full fault-tolerant quantum computer will not be there in 2 years, but I think we are all working very hard on having it available in maybe 2 decades. So I'm typically more optimistic. So I hope maybe in a decade or so, we can see some really nice achievements.
Perfect. Thank you so much. Are there any further questions? I don't see any more raised hands or more questions. So thank you very much, Claudius, for your insightful presentation. Yeah, with that, I would like to invite our next distinguished speaker, who is Artem Nikitin, Head of Sales at Delft Circuits, who will also discuss the topic of a possible route to scalable quantum computer. So,
Thank you. Give me a moment.
sure.
Share. Yes. Okay. All right. I hope you see my screen.
Yes.
So thank you, organizers, for having me on this panel. My name is Artem, and I represent company Delft Circuits from the Netherlands, from city of Delft, as you can imagine. And today I'm going to talk about a possible route to scalable quantum computer. Thanks for Claudius for a very nice introduction on enabling technologies. So that's exactly my topic today. And also I will focus only on scalability part, not talking about qubits themselves, and mostly about cryogenic part of it. Yeah. Let me address the issue in scalability of quantum computing systems. So here on the right, you have an image or photograph of roughly 50 superconducting qubit device machine, and also low temperature part of it. What you see is basically a bunch of coaxial cables, this spaghetti of cables, which dominates the low temperature but also intermediate temperature stages. And that's already an indication of a problem. Once you start thinking about thousands or maybe hundreds of thousands of physical qubits, the wiring actually problem become very, very serious. Yeah. So there is a quite serious bottleneck in the realization of quantum computing hardware, which I would like to address today. But let's first take a step back and see a little bit on different architectures. So today there are multiple architectures to realize the qubits. Yeah, and here I show only the most important, in my opinion, the 5 ones, but there are more exotic architectures being showing up from time to time. And according to some financial reports, one of the biggest players today are focusing their budgets in superconducting qubit devices. These include leading players like IBM, Google, and IQM, and Alice and Bob. And today, this is one of the most promising technologies in realizing the quantum computing. But there are plenty of others. For example, photonics qubits are quite scalable in terms of room temperature electronics, yeah, and we have big players here which are building huge systems like say Quantum and Xanadu. Neutral atoms and trapped ions are also quite serious. So IonQ is already publicly traded company today, and they're building many systems, including in Europe already. And QEra, as you have seen in the news, got a lot of funding recently. And we have European players as well as Pascal. And there are some hidden horses which are not yet super active, but very promising, like spin qubits. One of them example here is Intel, who is exploring actively the semiconducting devices and yeah, possibility of computing on silicon or germanium nanodots. Today, I'm gonna mostly focus on superconducting qubit architectures and how to help scaling the qubit numbers. But some of these lessons can be applied in spin qubit systems and, for example, detect a readout of photonic devices. Okay. So what's challenging here is coming from the qubits themselves. Basically, today each superconducting qubit requires around 3 connections to room temperature electronics. Yeah. So and these connections or channels are high frequency. So they are highly filtered high frequency signals which have to be delivered from room temperature, let's say generators, to millikelvin temperatures. And that's a challenge by itself due to enormous heat this signal bring, yes, and space also constraints. So the cryostats typically are relatively small, yeah. So you can build maybe up to 2 meter in diameter a cryogenic setup at reasonable costs, but bigger than that is very, very hard. So there is, let's say, the space limit, and then there is also the thermal load limit, yeah. So the heat load problem, because it's very basically inefficient machine to cool down such a big amount of metals. There is a lot of heat load losses in meantime. So physical footprint is very serious issue. Thermal load, installation. So once you talk about multiple types of RF lines, and in giving the fact that, let's say, each qubit needs different, up to 3 types of them, it's not just a wire, right? You have also some sort of filtering, let's say cutoff frequencies or attenuation profiles. This installation by itself become a quite a serious challenge, which requires often a team of engineers working in integrator companies to operate these machines. And very important part is the cost as well. So the cost of this setup is today valued around 10,000 euro per qubit for cryogenic wiring and filtering, which, let's say, if you're talking about a 100,000 qubit machine, yeah, the budget goes to the roof. So this is also a very important aspect. And a lot of points of failure. It's quite coaxial cables assemblies are quite fragile and very dedicated, very delicate hardware. So it's very expensive to break, basically. But don't worry, there is a solution here, and Dell Circuits has developed a CryoFlex solution which will resolve all these barriers which I just mentioned to you. And the CryoFlex is cryogenic flexible I/O, and I/O is input-output signal, so delivering signal in and delivering signal out from room temperature to millikelvin with signal conditioning integrated on Flex. And you see here examples of our cryogenic cable in the real system. So what is CryoFlex? So CryoFlex combines multi-channel signal propagation into one ribbon, basically. So we deposit multiple layers of metals into flexible substrate, which eventually deliver signal from room temperature. You see 300 Kelvin, sorry, 300 Kelvin room temperature electronics. It can go through the vacuum barrier, yeah, to go inside of cryogenic systems. It has signal conditioning integrated. So basically we have special structures embedded within the flex itself, so which allows for certain filtering type like low pass filter, attenuation, and infrared filtering integration. We use multiple metals one of them, let's say, is superconducting platform, niobium titanium, which often used for temperatures below 4 Kelvin for certain type of lines. And we also offer integration with the quantum device or chip. Yeah. So all of that eventually unleashes the possibilities to scale. So again, Cryoflex has a unique flexible superconducting technology, which is niobium titanium. So I think today Delsox is the player on the planet which can do this. It's very hard to. I don't think it's actually possible to find superconducting flexible circuits. Yes, with integrated on flex filtering. So it's basically instead of having up to 10 different components, you can integrate, or we can integrate everything in one setup. So what you can see here, like 19 strip lines replaces 150 coaxial cables, which are needed to connect up to 50 qubits. So number of components in your cryo start decreasing, basically, yeah? which eventually simplifies the installation process, reduces the physical footprint so it actually directly corresponds to thermal load. So because the thermal load is directly proportional to the volume of the metal inside of the cryostat. And eventually at scale, we're talking about reducing the costs. And by reducing the cost, I mean seriously reducing the cost by order of magnitude, yeah, compared to conventional coaxial cable solution. In order to summarize a little bit of what is possible, we're talking here again about multi-channel flexible circuits. So we bring in one ribbon, many channels, and currently we're talking about 8 channels per flex, but in the future we will be able to increase the density and to bring way more channels in one, let's say, multi-channel cable. We have a library of components possible to integrate on flex, which means that we can cover all input lines for superconducting circuits, for spin qubit circuits, and some parts of output lines can be also realized on our Cryoflex. And here we're talking about only about passive components. There are, of course, in cryostats quite a few of active components which are needed to be interfaced, and I'm not really talking about them in this presentation. Yeah. If you think this is technology just a dream, it's not the case. So we have successful integration already of multiple customer side. For example, the first quantum computer of Spain is using this technology. And as we speak, there are upgrades being going on in Barcelona Supercomputing Center. And we're doing that with our friends from Kilimanjaro Quantum Technologies in Spain. Surprisingly, we found out that in some non-quantum applications, our solution can bring the value. For example, in astrophysics applications, some of the detectors are using similar bandwidth as the superconducting qubits, and there our solution can actually help. And of course, we are working with, I would say, all of cryogenic manufacturers of Western world to make sure that their systems will include our technology in already now or in near future, and some examples sitting in this room already. And we hope to make sure that, let's say, the end user or the customer would not really care about where they source the flexible cables. So it should come from, let's say, cryogenic manufacturer as well as from us. To conclude, Delsox is a young and ambitious company with today more than 40 people already, with 25% women from 13 nationalities. We're based in Delft in the Netherlands, and we have a wide range of experience coming from RF world, from metal deposition, but also cryogenic experts and general physics experts. And what's important for us, we have really interesting investors which value our work. So ASML and Philips are investors of Dell Circuits, which shows that the Dutch semiconductor industry is actually actively looking into quantum, and we're very proud of that, and we're thankful for them for their support. In that note, I would like to conclude my presentation.
Thank you, Artem, for your insightful contributions. Indeed, a very interesting information on quantum computers that you shared. Let me briefly. Oh, I would like to open the floor for more questions. I currently see no questions in the Q&A box. Oh, I see a raised hand from Hesam.
Yeah,
Hesam?
yeah, thanks for the very interesting talk. I would actually kind of, let's say, ask you the same question you asked Claudius before. So you mentioned already, let's say, in your talk, how to go or how this the road for having multi-channel, but can you maybe comment a little bit more on that? So if you want to have really, let's say, real-world applications and thinking about thousands and even millions of qubits, so how does your solution scale?
Yeah, thank you for a great question. Indeed, we are thinking about, let's say, bringing tens of thousands of RF channels into the conventional DIL fridges, dilution refrigerators. Let me show you one image of that. Yeah, I'll start with this image. So this is, let's say, a commercial dilution refrigerator, which is already relatively big. And the limit today in coaxial cable assemblies is roughly maybe 3,000 RF connections to bring into the one system, which corresponds basically to roughly 1,000 qubits. So 1 kilocubit device. Yeah. So we can bring at least one order of magnitude high more connections. So I'm talking about 30,000 RF connections into conventional cryostats, which does not need to be modified, which eventually will bring us to 10,000 qubit devices. And we're already developing solution how to miniaturize, put, let's say, more channels into one ribbon, make it more compact, while, let's say, taking care of crosstalk. Obviously, that's one of the limiting factor. And we believe that we can increase that number by another order of magnitude in a relatively straightforward way. So we're talking about 300,000 RF connections in, again, conventional cryogenic setups, which will brings you to roughly 100,000 of qubits. So how to go to a million qubits? Yeah, that's another story. But we see already direct path towards 100,000 physical devices at millikelvin temperatures.
Yeah, very impressive. Thanks.
Thank you for this question, Hesam. Let me quickly check the comment section, but as far as I see, there are no further questions. So thank you very much.
I think Jan has a question.
Oh,
maybe
sorry.
for Claudius and Artem. So you're talking about now cryogenic cabling, right? So how can I imagine this to happen then at room temperature? So right now, I think there's a lot of focus on the cryogenic cabling, but out of the cryostat, there's SMA. Where do we go?
Yeah, that's a great question. We always say that at room temperature there is more space, but it's not entirely true, yeah, because there is a ceiling. And I don't know if I have image. No, I don't have really image of room temperature, but yeah, something has to happen there for sure. And one way forward, yeah, okay. Yeah, Claudius, maybe you can comment. Yeah.
Yeah, maybe I can also be more concrete. We are working, for example, in a joint project in QSolid. There is Rosenberger came up with those new GaN connectors on SMLP. So this is already significantly smaller than SMA, and you can connect multiple cables at the same time, because I think we all agree that going for 10,000 of SMA connectors, which you have all connect with a spanner wrench, we should not make any user do that. So also not PhD students. I have very strong opinion there. So I think there there are many solutions being worked on at the moment. And of course, now we need to bring, for example, Artem's technology together with those solutions. But I think this is very feasible in the future.
Thank you.
Thank you very much for this insightful exchange. Are there any further questions? Nope. As far as I see, there are also no questions in the comment section. So thank you very much, Artem, for again this insightful presentation and contribution. We can now move to our next esteemed speaker for today's quantum leadership session, which is namely Clemens Schäfermeier, who is the principal scientist at Adacube Systems, and who will present his insights on cryogenics becoming a commodity. So there you go. The floor is yours.
Thank you. Thank you for your kind introduction. Let me share my screen and let me know if that works. Can you see my screen?
Yes.
Okay, thank you. So thanks again. Good afternoon. Thank you for your very kind invitation and to ask me about my opinion in this field. And I do, as a member of QBN, really do appreciate this platform to connect different fields, different company, different young startups, and also researchers that have a keen interest and keen eye on bringing quantum technologies much deeper into industry, into real world applications. So yeah, I will talk about cryostats, and the scope of my talk will be a little bit different than the previous ones. So let me say a few words about Adacube in the first place. So Adacube is now a bit more than 20 years old, in fact, and it is really deeply rooted in the whole quantum research, I should rather say, area, starting with nanopositioners, with SNOM systems, and then also after a few years developing and selling cryostats. And while a few or most of these products have been out there, or technologies have been out there, a focus of Adacube was always to make things a bit more robust and a bit more user-friendly, and incrementally improving the robustness, the user-friendliness, and as also Artem pointed out, especially when it comes to cryostats, the scalability, the serviceability, the installation, that is still something that has potential to improve. So yeah, while Adacube is a bit more than 20 years old, I'm working for Adacube now a bit more than 7 years, and my role both covers, let's say, the technical aspects, to have a look, to test, to discover new technologies that might be interesting for our customers, but also to have a look at the market side and to serve new markets with novel technologies, but also to serve new markets with existing technologies, existing products that we have, but just serve them for their own application that is not so much as obvious as it might seem. And that is true for cryostats as it is for nanopositioners. Let's say you might think of a nanopositioner in the cryostat, but just works as well in a biological setting, let's say. And so before I start with my first slide, I should also say that I was asked to not make this a marketing presentation. So if you feel after my presentation the urge to buy a cryostat, then I certainly failed, and I'm happy for your feedback to tell me where I made this a very compelling investment. And so talking about cryostats, what I mean is that what is a cryostat? And a very simple definition is it's only a cryostat if it's cooler than the boiling point of liquid nitrogen. That might seem to be a little bit arbitrary, but this is just what I stick to. So, and I'm going to just list a few, let's say, key areas where do we see the use of cryostat, and I'm trying to answer here the question, which might seem to be a little bit funny, but some other people might know about this way of questioning a product. So I'm asking the question, why do you hire a cryostat? And let's classify the jobs of a cryostat. And I do find these three main areas. And the main areas, let me say that, are not by, let's say, don't have a physical significance. So you might say that, let me pull up the pointer here. There's no real difference between superconductivity and reaching a ground state, a quantum mechanical ground state. But in terms of the resources, in terms of the requirements that you need, there's a certain difference that we see. So let me start maybe on the right-hand side. We do see a need of cryostats as a cold trap, or let's say as a vacuum pump, especially for neutral atom or ion-based quantum computers. And the special requirement here is that there's not so much the need for reaching ultra-low temperatures, but you need to be able to cool your vacuum chamber, your chip. You need to cool down several nanopositioners potentially. And so you do have, or you do face a significant amount of heat load. And while companies or users might be totally happy with 15 Kelvin, they might want to have 10 watts of cooling power, let's say. Then we have the job of superconductivity, and maybe the first one that comes to mind on more general terms is MRIs. But MRI systems are large and are very specific. So entering the market of MRIs as a cryostat company might be rather difficult. And also for the audience here in the QBN, something like superconducting nanowires single photon detectors, so the SNSPDs, are much more familiar and much more easier, much more appealing in a sense of applying them in quantum communication, quantum cryptography. So these kind of devices are devices that you find in most of the commercial products nowadays. Squids are another type of products of technologies that need low temperatures, and you find them in devices for magnetic field or magnetic flux sensing. There are a couple of startups providing you with chips that are equipped with squids, so you can measure, you can map out fields with a resolution of less than 100 nanometer, and you're very sensitive. You can apply them, let's say, for instance, for fault detection of electronics. And there's also an emerging field of putting electronics either for low noise purposes or for energy saving purposes in a cryostat. And then finally, the last pillar here is to reach near a quantum mechanical ground state. And then, of course, you have a lot of fundamental research, also that the AtoCube and other cryostat companies are serving. You have material science, which is maybe in that research aspect the most mature one, because it typically aims at applications. And then you have the superconducting-based quantum computing, where we already heard two very nice talks about. And the only difference between, or the reason why I put the superconducting-based quantum computing here in this pillar, is because you are much more concerned about reaching really low temperatures than just reaching the point where you are superconducting. All right. And so I like to motivate this need for cryostats in a bit more general way. And one way that I think is the most general maybe is to look at a graph that simply links the frequency to the temperature of a given system. So you always find yourself on this x-axis here somewhere if you're working with light, if you're working with microwave or RF components, and you can link this to a temperature. And the way I did this here is simply by saying, okay, take a given frequency of your system, of your qubit, of your harmonic oscillator, and link this to the temperature of a system of a thermal state, and it has one quantum of energy. So let's say we do this for microwave frequency, and the regime that I marked here is, let's say, from 300 megahertz to 300 gigahertz. You might shift this to the left or to the right, depending on your liking. And the highlighted region here is somewhere around the 10 gigahertz for typical superconducting qubits. On the lower end, you find RF circuits or RF electronics. And here you can see that if you have something below 300 megahertz, then you are already deep down in the millikelvin and even microkelvin regime, if you want to talk about single quanta. And so, again, if we zoom in this graph a bit more on the microwave regime, something that is quite easy to remember is always this point of 1 Kelvin. So here we have 20 gigahertz roundabout of a frequency, let's say of a qubit, and then the temperature such a quantum bit, let's say, has is 1 Kelvin. Now, if you add the optical regime, then even for 1550 nanometer, which is a typical telecom wavelength, such an energy or temperature equivalent is something like 10,000 Kelvin. So you are significantly higher and you are significantly above room temperature. Now, one thing that is very important here in this graph, and that might be a little bit misleading, is that it might tell you that, well, I mean, millikelvin can be easily circumvented if you just go a little bit higher in temperature, right? I said 20 gigahertz is about 1 Kelvin, but your qubit is sitting in a thermal bath, and what you want to make sure is that there are no excitation transferred from your thermal bath to your qubit system. So you want to protect it. And let's say a rule of thumb, you want to make sure that your thermal bath is, let's say, a factor of 1,000 cooler than your qubit. So you need to cool down everything. And it's rather easy to calculate this with the Boltzmann distribution. And here you can see, let's say, if we say, if we focus on the superconducting qubits, you are now not talking about a Kelvin or 0.1, but you are talking about something like 10, 20, 30 millikelvin. However, if you do have the choice to use any kind of frequency or to build your qubit, then a threat, so to speak, or there's a typo here, should be T, for a qubit system, for cryostats, is photons, is photonic circuits. And there might be a need, or there might be a good reason why you go into optics for quantum bits. And the reason why that is, we'll see hopefully in a few slides from here. Now, you might ask a question, especially if one is not so familiar with the whole plethora of cryostats that you have, how big is the market here? And one way to assess the size of the market is simply to look at all the options that you have. And so you'll see now 3 slides for different categories of cryostats. So you have the top loading cryostats first, which are typically a vacuum vessel. You often find a superconducting vector magnet inside, interesting for material research, let's say. And inside you have a sample chamber. Sample chamber might be in vacuum, might be an exchange gas, and then you come and load your stick, your microscope stick inside the cryostat. And the stick might be anything between half a meter to a meter long. And while this might be a little bit difficult to access optically, it typically provides you with the lowest temperatures and it can also provide you with very high magnetic fields if needed. Furthermore, if you're interested in very high cooling power, then these systems potentially also have the highest cooling power. So for RF or for microwave circuits, then you certainly need to have a millikelvin cryostat, as we learned before. And there's also quite an option of companies, and more companies also entering this market here. And finally, you have a category of tabletop cryostats, which are especially interesting for you if you do want to interface a cryostat with optics. Now, of course, this is something that you might still see rather in research labs than in actual industrial settings, unless you have a very compact optical breadboard or optical table. And now let me say a little bit about AtoCube's portfolio. So we do serve all three markets, while the millikelvin market is served in the sense that we collaborate with millikelvin companies providing millikelvin cryostats. And well, our two, let's say, main workhorses are the 21, the 2200, which are top-loading cryostats that feature up to 9 Tesla vector magnets. We have a tabletop cryostat, or we have two, one housed in a typical optical platform, a typical optical breadboard, and one called the XS version is basically about the width of 19-inch rack and a little bit deeper than that. And our latest product is the compact mobile cryostat, which is used by a couple of companies, especially doing SNSPDs, what I mentioned earlier. But you can also use the compressor itself to drive the cryostat on an optical table. And that might be interesting for you, especially if you have limited space, limited lab space, because as you see on a later photo, actually, the supply units that you typically need to drive one of these cryostats is quite significant in space, in supply units, and in electricity. So talking about commodity, because that was part of the title of my talk, where are we today? So how easy is it to use a cryostat? So on the left-hand side, and here again, I'm using AtoCube products or AtoCube photos. You see the cold plate of a top load, of a tabletop-based cryostat. The cold plate is this golden disc here. You can load positioners on it, a sample, and there's an objective here for optical access. You put 2 shrouds on top of it, and then you do find yourself presented with a web interface that can be accessed remotely via the internet, and you can cool down the sample. You can perform sample exchange. You can set a certain temperature, dial in magnetic fields. All of that, remotely with any kind of web interface. So comparing this to, well, even let's say a decade or 2 decades ago, there is quite a significant step here in terms of user friendliness. And again, AtoCube is not the only company who's doing that, and it's focusing on this user friendliness. Because even I remember that during my PhD, you had open cryostats, liquid cryostats that had to be filled in the morning with helium, and then you were measuring, let's say, 8 to 10 hours, had to wait another day and then refill the helium and so on. And nowadays, the systems are easy to use, are dry, are closed cycle. But on the other hand, if you look into publication and research, there is still quite a lot of competition and publication on alternative aspects of cooling. And why that is might be on another page, but let's see what are potential competitors for cryostats. So there is laser cooling, and there are several ways to implement such a laser cooling technique, and you can also, for small systems, reach significantly lower temperatures. There is feedback cooling, and there are various implementations of feedback cooling. So let's say if you have a membrane, an optomechanical system that you want to cool down, you can use, for instance, dielectric gradient force. And if your membrane moves to the left, you attract to the right. And if you do it in a closed loop way, you can freeze out the motion of this membrane, for instance, and bring it close to quantum mechanical ground state without any need for a cryostat. And then finally, a big topic is, of course, material design. So people might call it metamaterials, bandgap engineering, and so on. And there are several publications that aim to provide single photon detection with very high efficiency, even at room temperature. Also, to name maybe some emitters. So I'm showing here the structure of silicon vacancy center and diamond. There are several decoherence channels of such a silicon vacancy center and diamond, and they take place at about 50 gigahertz. Now, let's say 50 gigahertz in diamond corresponds to about 120, 130 nanometer. So if you put the silicon vacancy center in a very small diamond, smaller than this 120, 130 nanometer, you inhibit all of these decoherence channels, and you also get a very high coherence of your emitter without the need of a cryostat. And so if you look into why that is, again, there are other reasons why you want to use one of these techniques. It's often that you circumvent the need of a cryostat, because feedback cooling, at least for very high frequency resonators, could be also achieved just as well with the millikelvin dilution refrigerator. Of course, a drawback here is that these techniques only focus on on very, very few modes of vibration, let's say, and they don't cool the bulk. But if you just need to cool down a certain mode, then this is probably something more efficient. So the question is, why do people focus on that? I mean, I've shown you this photo of this nice, clean cryostat and this web interface and so on. So why are there competitors? And here's just like one example where we came from. Right? This is a liquid. This is a flow cryostat in operation, and this operates as long as you have liquid helium flowing through your pipe. You need to recollect it, recondense it, and so on. So this is a lot of hassle. And as I said, we came a long way from there. But also, you have to keep in mind that nowadays, this is one of our cryostats in installation. I mean, apart from the person here taking a photo, you see probably like 6 hands here, 3 pairs, to install such a system. And this is the mentioned support unit, which does consume quite a lot of energy, water, and, well, eventually money. So there is still something to do to make it more efficient, more robust, and so on. And our approach is what I said, the ATO CMC, the compact mobile cryostat, at least for certain applications. And so now opening this up for a bit more and making sure that the cryostat business remains a business also for the next decades, or for the 2 next decades, for more than just the quantum, for the superconducting quantum bits. What can we do? And well, I don't have an answer to that, let's say, at least technically, but we might get an idea where we have to look at and where we have to go to, because this is a problem that basically any kind of market faces, any kind of product faces that. And what I'm drawing here is a chart, it's a graph that is first created or found by Clay Christensen. And what it shows is that how the mainstream market, how the user increases its demand on the product performance. So over time, we all like to see our computer, our whatever, our guitar, our cryostat to increase in its performance, because we all become a little bit more ambitious. We do see there are competitors and so on. And there's more and more that the mainstream can utilize. You have a high-end market for very high-priced products, and there's a low-end market. And well, typically what companies do, and incumbent companies, so companies that are already well established, is to say, well, we're trying to aim at this eventually also at the high market, because the high-end market is the market which is most profitable. And it's also in some sense the most secure, because you have the least amount of competition. So the better you are, the less competition and the higher the price you can ask for. And now if we would just follow this, we would be probably stuck with with closed cycle top loading cryostats for the next 2 or 3 decades. But the problem is that other technologies might come around and make such a type of cryostat redundant. So to make this market of cryostats sustainable, you might have to think of something that is disruptive. And disruptive, by the definition of Clay Christensen, is a technology that doesn't aim at the high-end market in the beginning. It's rather something that aims at the low end or is even below the low-end market. And is typically something that has even no competitors in the beginning. But on the other hand, it's something that's robust, that's simple, and that is cheap. And just as the incumbent company increases its product performance over time, the disruptive company, the entrant company, is doing the same. But it has no competition, because the incumbent companies as well, they are so bad, their product performance is so poor, it's simply no competition for us. But over time, what happens is that the disruptive innovation will appeal to the mainstream. And at this point, the disruptive product has been has matured to a point where it beats the incumbent company, the incumbent product, in every aspect, and especially in the aspect of robustness and usability. And well, again, as I said, we're trying to appeal to this by the ATO CMC. But if you have any other ideas, I'm more than happy to collaborate, to have an open ear on that. And I thank you for your attention.
Thank you. Thank you very much, Clemens, for your insightful presentation on cryogenics. I see 2 questions in the live YouTube comment section, so let me read them out. The first one is, are there any emerging industrial applications where those compact cryostats are becoming more relevant?
Yeah, so the one that we see today the most is anything related to quantum communication, quantum cryptography. So superconducting nanowire signal photon detectors in general, and also embedding active electronics into it. And well, if you sell a system for quantum cryptography, those systems are typically rather compact. You have an emitter, you have a source, you have some electronics that can easily fit into your 19-inch rack, and you don't want to add to this a super bulky, a loud, noisy, energy-consuming support unit. So for this market, a compact and a mobile cryostat is key, because everything fits into your rack, and you don't need things like water supply or high currents. So this is a market which is, I wouldn't say necessarily established, but which is still emerging. And well, established is probably more the one for cryptography or communication. What is more and more emerging is then also the market for of companies making using qubits, using optical qubits for quantum computation. But then again, that can be boiled down to superconducting photodetectors.
Thank you. There's one more question related actually to the first one as well. So in the presentation, it was mentioned that for frequency of around 20 gigahertz, the temperature equivalent is about 1 Kelvin. And does this relationship hold linearly across different frequency ranges, or does it vary?
This one here. Right, this simple graph. I mean, again, this simple graph is simply to say you relate Boltzmann constant and the temperature to the frequency and Planck's constant, and that's it, and that's a linear relation.
Okay, thank you very much. I also see one raised hand by Haysam.
Thank you very much for this great talk. I have one question regarding, I mean, you mentioned that your devices are they can be very mobile and they can be very compact and robust. So can I, for example, also imagine maybe, let's say, having drones, let's say for quantum communication and let's say flying around, so also upside down. So are all these things also possible with your cryostats, or are there some limitations then?
Right. I mean, there are a couple of let's say, at least research applications where these CMCs are airborne. And airborne means rather, let's say, a helicopter or a plane. But if your drone has a payload that is more than a kilogram, then this is absolutely feasible. And probably what the drone has to carry on top of the cryostat is a significant. It's just a large battery, right, to provide the power for it. But also to be clear about this, the CMC you can just use any kind of wall plug to power this.
Thank you. I also see one additional raised hand by Jan.
Yeah, sorry. One question concerning, you said that you enter this market with this product probably you see it as a disruptive technology, right? And so I gather from this that you're actively working on improving specs to get it into to give it more use for the customer. Is this also related to that you want to increase the cooling power based on this igloo compressor technology?
Yeah, right. Yeah, and exactly. So we call the compressor unit itself. So this box here underneath, that is what we call the igloo compressor. And again, the specification or classification of what is disruptive, what is incremental is always a little bit difficult. When is it really correct to call it like that? There's often a debate about this. But what we try to exploit is this very, very energy consuming, energy efficient and space efficient technology, and yes, make it even more efficient to get more cooling power out of it. You could also think of combining two igloo compressors, but then again, you just have a linear scaling, right? You don't, and that's an obvious one. You don't win. It's only a real improvement if you have some I don't know, quadratic or whatever improvement.
Mm-hmm. Okay, great. Thank you.
Thank you very much, everyone, for this insightful exchange of opinions and this discussion. I don't see any more questions, so I would like to invite our next distinguished speaker, namely Jan Spalek, the co-founder and the CTO of Qtre, who will discuss the topic of cryogenics from fast characterization to large-scale operation of quantum circuits. So there you go.
Just share my screen. Can you see it?
Not yet. Yes, right now, yes.
Okay, great. So hi, I'm Jan Spalek, CTO and co-founder of Qtra. And today I'll be talking about the fast characterization, from fast characterization to large-scale operation of quantum circuits. We will have heard a few of the things that I will say now already from others. I think one or two graphs probably are now from all different sides, but let me first say something to Qtra. So Qtra is a startup founded in 2018 as a spin-off from Technical University of Munich, where all the co-founders came essentially from a chair that did low temperature research. We've grown quite significantly, so we are now more than 60 people who work on our products, and we are based in Munich. We have about 1,500 square meter of office and production facility where all of our cryosets that we build are designed, built, and then shipped from, and we've shipped to 48 customers all over the world by now. So what I want to talk about, I want to give a very short introduction on cryogenic technologies in quantum, where we have heard some stuff of this already. We will be identifying a few critical bottlenecks that we see for the future of cryogenics in this space. And we see some approaches on how to tackle these bottlenecks. More to that later. So in quantum, the development of quantum chips is accelerating quite quickly. We have seen this multiple times today already in different talks. There's a lot of movement in the quantum space, and we have come to a point where I can easily grow a wafer of a few hundred, or even a few thousand, or even a few 10,000 qubits. But then what do I do with them? I need to characterize. The yield is not as good as you want it to be. So this leads to the fact that many of the technologies that we are that are being investigated as qubits are no longer slowed only by the engineering of the qubit itself, but we're also approaching a bottleneck in testing, which we'll come to later. And this also means that the enabling technologies, namely, you can see here on the right, cryogenics, photonics, control electronics, to name a few, are becoming more and more crucial to the continued advance in quantum technologies. However, it is not clear yet which kind of qubit implementation will really win. And this results in a quite broad spectrum, as we can see here today as well, I guess, with the speakers that are here, of enabling technologies that might be critical to allowing the scaling. So this can be cryogenics for quantum communications, for example. It can be photonics, like was mentioned before, for photonic quantum computing. It can be control electronics, or it can be all of these together, or some technologies might only use subsets of these, right? So we build cryosets, so we're naturally interested in the temperature that these technologies run on. We have seen this already very similar, I think, from Artem before this slide. We have superconducting qubits by Google, IBM, Alice and Bob, which run in the dilution refrigerator at 8 to 50 millikelvin normally. We have the quantum dots, or semiconducting qubits, as they're called, by Intel and Quantum Motion, for example, which run a bit warmer in the range from 100 millikelvin to 4 Kelvin, whereas normally they run rather in the 100 millikelvin range than the 4 Kelvin range, at least until now. We have photonics, so photonic quantum computers that run in the 2 to 4K, where the photonic chip itself does not necessarily need to be cold, but most of the players utilize the single photon detectors that were mentioned before as well. And then, as also mentioned before, we have the controlled atoms, namely trapped ions and cold atoms, which use the cryogenics not for cooling the chip or any detector, but to really cool the, say, surroundings to provide a very good vacuum to optimize operation of these systems. So now to take a quick look. So I mean, this is not definitely not all of the technologies that are there, and changes from time to time what they need and what they don't need. This depends also on scaling, of course. But we want to look here because we build, say, sub-Kelvin systems mostly. We want to take a look at or focus a bit on the superconducting and the semiconducting qubits here. Next point, how do we even get to these temperatures? So we've heard talk about today dilution refrigerators. We have heard talk about mechanical cryocoolers, or like the Atto CMC, for example. So the rough graph of technologies that are used nowadays to reach this kind of temperatures, we can see that we have the helium-4 bath cryostat, which is actually not really used anymore, like Clemens mentioned before as well. This has mostly been supplanted by the mechanical cryocooler, which can provide temperatures down to 1.8, I think is the limit where you can usefully use them at rather high cooling power compared to the lower temperature technologies. Then if we want to need to go down further in temperature, we have the helium-3 JT coolers, which is normally then paired with a dilution refrigerator to reach temperatures in the single-digit millikelvin range. The same range we have adiabatic demagnetization refrigerators, which reach similar temperatures, a bit warmer, but at significantly reduced cooling power in comparison. The dilution refrigerator is the state of the art. We have seen this, I think, in Artem's talk in the beginning. That is where most of the low temperature quantum computing happens today. Then for completeness, we also have laser cooling, which technically cools the individual atoms or ions to extremely low temperatures, which makes saying it is running at room temperature a bit questionable, but yeah. So you cool on the level of individual atoms, essentially, right? So until now, most of these developments have really taken place in an academic background. Yes, so most of the advances in quantum computing have been made in academic labs, where we have the classic, like was also mentioned before. We have PhD students. We have very different timelines. We have a different way of working, essentially. But we are approaching rapidly a point where we see that we are going from an academic context to a more industrialized context, which is where we need to take a look again at the cryogenic systems and really say, okay, what are features that maybe before I did not care about in an academic setup, or it was not a deal breaker in an academic setup, but it will be a significant problem in down the line in an industrialized setup. This is true for all technologies, not only quantum computing, but also quantum communication, quantum sensing. You need to look at it in a different way. We have heard this from Claudius in the beginning. It needs to be reliable. It needs to just work, right? So we see there are some critical of these points here that are listed, namely it's the speed. We need much faster feedback, and we want it much sooner after testing something out. We also see problems in level of automation. Clemens was also mentioning this. There has been huge strides in the automation and usability of these systems, but there's still quite some way to go, I think. Then we have scalability, we have energy consumption, we have investments, so CAPEX and OPEX, essentially. How much do I need to pay for it, and how much is it of my whole system? Yeah. So we have then identified from these two bottlenecks. One is the combination of speed and the level of automation, right? This is what we call the characterization bottleneck, and this is where we are in right now. So we see that the development speed is significantly affected by the long cooldown times, for example, of state-of-the-art machines. We see also that complex workflows occupy a lot of the scarce quantum workforce. So you use quantum engineers that should do qubit designs or should do high fidelity measurements. You see opening and closing radiation shields. This is not where you want to spend your resources on. So also that parallelization, which is happening right now, to actually implement this kind of testing that is needed, requires a rather large investment in auxiliary electronics and components. So that is the characterization bottleneck where we see right now and where our customers mostly come from, and this is why they buy our products. Down the line, we see a scaling bottleneck based on obviously the scalability, the energy consumption, and cost. So if you imagine quantum computers being not built in the single-digit numbers, but in hundreds or thousands, we see that the existing technology, namely the dilution refrigerator, which is dependent on helium-3 supply, will create a bottleneck, especially if you don't have direct access to helium-3, which is only really supplied from the US, Russia, and Canada. For example, there's no real source in Europe. We also see that large-scale systems for operating tens of thousands of qubits have not yet been engineered at all. So when Artem showed his cabling, this can definitely reduce this problem, but still they are not here yet. And we still also see that cryogenic systems are one of the main drivers for cost in quantum technologies in general. At the same time, we see that development of cryogenics is gaining momentum. Clemens also mentioned this before. We see this especially in that there's many new startups and many new companies entering the space. Some examples here, like 0 Point Cryogenics, Mabel, 49 Design, that showed up in very recent years and show that cryogenics is becoming more and more, maybe also commoditized. We all see at the same time that there's quite some movement in established companies, namely, for example, FormFactor, which is focused on semiconductor testing, bought Janus low temperature systems. So they also have now dilution refrigerators in their portfolio. At the same time, we see that Bluefors partnered with Devco to gain capital for further growth in this market. So these bottlenecks are recognized. There are some solutions that are coming up. So we see that the scale-up bottleneck is addressed by, for example, here, Bluefors and Mabel that build these huge refrigerators. I mean, the picture that you see here, the Bluefors Kida is, I think, 3 by 3 meters in. So the hexagon is like 3 meters in diameter, and it's, I don't know, 3 or 4 meters high. So it's quite a significant machine, and it will hold a lot of cabling and a lot of qubits. But and they are also designed to be scalable. So there's progress there. We also see at the same time the characterization is being recognized as well. So we see a lot of new players offering small dilution refrigerators that promise more flexible operation, and they are gaining more traction. Especially there is a lot of talk about high throughput. So how does Qtra do it? We do it a bit differently. So we use what is called the adiabatic demagnetization refrigeration, so magnetic cooling, compared to a say dilution refrigerator where you this is based on a dilution effect of the helium-3 and helium-4 isotopes. We use a magnetic field for cooling. Very easily said, we have a solid state cooling medium. We apply a magnetic field to it using a superconducting magnet. It heats up. We dissipate this heat to a pre-cooling device, and then we remove the magnetic field and it cools. Of course, the technical implementation is a bit more complex, but that's essentially it. And this brings with it an inherent scalability. We are not dependent on any strategic resources, so we can build these systems completely helium-3 free. At the same time, we pair this with smart engineering. And for example, our patented sample loader allows for very, very quick cycle times of samples. Like others here, we focus on usability. So we try to envision and define workflows that minimize human interaction. So like said before, the expensive quantum engineer does not have to open radiation shields and play with the cryostat, but just can focus on the stuff that he was hired to do, let's say. We also try to package standard measurement options into packages that can be sold as state-of-the-art and just well, let's say to package state-of-the-art measurements in options that can be bought off the shelf, that then you don't have to reinvent the wheel every time you have a new system. At the same time, we also look at cryogenics as a service where we rent or provide services on devices that we have in-house, where we know how to operate them, we know how to implement the measurements, we have the people to do this, and you can just approach us and buy this service, either rent it yourself and come by, or have some of us do the measurement that you want. How do we implement this? We implement this using the L-Type Rapid. This is our flagship product. It's a fast testing characterization cryostat for quantum devices. It's fully automated, loading and operation. So you don't have to touch any cold part essentially of this cryostat ever if you keep it in operation. We call it technician ready. You get the full measurement setup pre-configured and tested in factory. So like RF lines, amplifiers, shielding will all be integrated already. You can start measuring essentially from day one. It supports a quite wide temperature range from 100 millikelvin to 300 Kelvin. We will be launching the 50 millikelvin version of this device next week at the APS. And show some stuff there, and still the fastest sub-Kelvin cryostat in the market that we know of. So it cools down the sample in less than 3 hours to base temperature and warms up, especially important in only 30 minutes. I talked about workflows before, so with this comes this workflow, just to give you an idea on how it works very briefly. It consists, so we have a puck. This is essentially where you mount your experiment, your whatever you want to characterize. We have a puck station, a transfer cage, and the sample loader itself. The sample loader sits on top of the cryostat permanently. And to load your experiment, you would first mount your sample on the puck. So you can plug this into the puck station, which gives you interfacing to do all kinds of tests that you need to do before you are sure that you want to load your sample. Then you take the transfer cage, you click it onto this puck, and inside this transfer cage, the puck is transferred inside the sample loader. At this point, you don't have to be present anymore. So this is all the interaction you really need to do in situ with the cryostat. So the next step can be done completely remotely. You tell the system to load, it will automatically transfer the sample inside the cryostat. And if you queued measurements, will also automatically do these measurements, which you can just monitor remotely. One example for this, how this goes, we did a qubit characterization of a partner qubit provided by Conscience. You can see here, let me take the pointer is gone. Okay, or do you see my mouse? No.
Yeah, we see the mouse, yes.
Okay, so you can see this here is the puck. This is a large puck version. We have the qubit on top in a small copper enclosure box. We have set up the cryostat with a standard cable tree for qubit characterization. So an attenuated input line with low pass and infrared filters, and then a non-attenuated output line with hemmed and triple junction isolator. We controlled all of this with the Quantum Machines Octave and OPX Plus. So what we do is we load this qubit, we do the measurements at 50 millikelvin and use the T1 time, relaxation time, as a benchmark of the qubit quality. We see here that we measure 50 microseconds, which is as expected from the qubit that we were given by the partner. You can see here we did in this specific experiment check how does additional shielding on the puck influence T1 times. So you can see that no puck shield, it's quite bad. If you just have a puck shield, it's better, but if you have puck shield and this has a special coating, you will get your full performance. And this kind of test you can essentially do in 2 days in multiple loading. So we take it out, we change whatever is on there, we load it back in. And the classical cooldown curve looks like this. So we have at 0.0, we have loading. It will drop quite quickly to about 80 Kelvin. And then over 1.5 hours, approximately, it will go to 4 Kelvin. We let it thermalize a bit, charge the ADR, and then go down to our final temperature to do the measurement. The workflow then looks as this. I already explained it. We have a measurement preparation, which is essentially you have to go to the cryostat and click into your puck into the transfer cage. It will do the automatic cool down to 50 millikelvin, and you can do the qubit initialization, which is essentially just finding the exact frequencies. There, I think it would be very interesting to see how fast this can be done. because this is a significant part of these 5 hours. We then can do a simple qubit characterization in 10 to 30 minutes, depending again on the algorithms we use. And then we can decide, okay, do we want to do a longer qubit characterization for more time, or do we want to warm up? The nice thing about the fast warm up is at any point when you see that the qubit is gone, for example, let's say I'm here and I don't find the qubit, I unload it, it takes 30 minutes and it's out. If it's broken, I can even say, I don't care about if it sees a bit of ice, it takes 5 minutes, but then it will be frozen. So that is one example for the workflows we try to establish, or we try to think about to use with our devices and try to facilitate to make this characterization bottleneck as small as possible. Additionally, like already mentioned, we offer services. So we have 3 devices, so 3 cryostats with measurement equipment now in our facilities in Munich, where especially startups, but essentially everyone can rent buy measurements or rent cryostat time, which can be used for just to fully outsource this, or it can also be used to just bridge delivery times. Some customers do this because they want to start straight away. Currently, we offer resistivity or voltage measurements, superconducting resonator, spectroscopy, IV curve measurements, and the qubit characterization will also be there, will be coming soon. So second bottleneck that we identified before, sorry, I need to go a bit fast. That we identified before is the scale up. So how do we scale this technology up that we can really use, like Artem also insinuated, or Claudius, go from thousands of qubits to hundreds of thousands to millions of qubits. So here again, we say we settle on inherent scalability. So we go with the ADR technology, independent of any critical resources. We stick with smart engineering, of course, because we have the people already, and we scale up cooling powers and base temperatures based on proven technology. So this you will see in a second what we have done in this direction already. We're also aiming here in this to really already think with the data center, for example, as a point of deployment from the get-go. As we design this from the ground up, we have here the chance to really make it fit. And we will have a large focus on modularity. So we will disconnect the chip and the wiring from the cryostat so they can be deployed independently. This is for, like you've seen also many pictures here of the dilution refrigerators where the qubits sit in at the moment. They are intrinsically connected, which is a problem if I let's say a chip provider like IQM, IBM, they want to commission a system somewhere, they need to buy the cryostat first, they need to commission it in their facilities, and then ship it with the whole cryostat and essentially do the commissioning of the cryostat there again. We aim to eliminate this problem and essentially take the cables and the chip away from the cryostat so it can be standalone. We did the first step on this in cooperation with Delft Circus by building the S-type quantum, which is geared towards the operation of quantum circuits, completely helium-3 free. So based on ADR technology, Delft Circuits provided here the cabling, and Qtra built the cryostat itself. Can be seen here, it offers 24 RF lines, which will allow us to operate a 5-qubit chip. We're currently working with IQM to make this showcase happen. It has quite a compact form factor, so you can see it is rack-based. This is 800 width, so it's not the small 19-inch rack, but the one step larger, but it's 800 by 800, so it will fit to any office door. It's quite convenient. Of course, the compressor for the cold head that pre-cools it is not included in this. So this is still like we saw also before for Clemens in the next room. And we reach with this base temperatures of 27 millikelvin continuously and 19 millikelvin in single shot. This was really based mostly on technology. I give you a short glimpse on what it looks like in here. This is the same technology that we use in the L-type rapid. So same superconducting magnets, same cooling media, same heat switches, But here it has now in total 4 ADR stages instead of the 2 that we use in the L-type rapid. And we also have some newly developed superconducting heat switches that is then all integrated into this lower part of the rack. Then we have here the sample area, so we have quite a large area for mounting of samples, and it's quite flexible. You can see here the dev circuits lines coming out, and then we have a third part for control electronics and everything else that we need to operate the system. And based on that, we are ready for the next step. So we've learned a lot in building this system. We're quite happy with the performance that it achieves now. So we have started a new project, which will be a scaled-up version of the S-type quantum, where we aim to build a full spec demonstrator by the end of by 2027. The development here is supported by approximately 4 million euros in the EIC Pathfinder Challenge on clean and efficient cooling. And the goal is to really extend this technology, this inherently scalable technology to replace the dilution refrigerator. So this demonstrator that we're building now is aiming to provide more than 20 microwatt at 20 millikelvin continuously. We're there at the moment. We're testing the first components. That's it. I hope I could give you a short glimpse on what Qtra is working on and what we see are the challenges, especially with regards to cryogenics, but also in general. If you're interested in any of these, just get in touch. We're also always open to join projects or alignment on development roadmaps, for example.
Thank you very much, Jan, for these insightful contributions. Indeed, very interesting information on cryogenics that you shared. I see no questions in the Q&A box, so I would invite, anyone here. I see Haysam's raised hand.
Yeah, thanks for the great talk. First maybe just a comment. I like that you also pointed out that for the sovereignty and especially looking at the geopolitical situation, these kind of solutions are very, very interesting, so that you're not dependent on the US and so on, let's say, rare resources. So I think this is also very, very important looking at the long run for computing and all the other technologies. And then you also mentioned sustainability, especially now in the end. Can you comment a little bit on that? So how sustainable is it, and maybe also compared to other solutions?
It's hard to say. So we are actively looking at sustainability. This is especially in regards to rare earth materials. It's mostly rare earth materials or other rare materials. We're of course looking at helium-3, where the classic definition of sustainability is not so the getting helium-3 doesn't harm anyone in principle. If you go around the fact that it's mostly gotten from hydrogen bombs. But we see that that we have also the possibility to reduce power input. So right now, this is not a focus in the development that we're doing. But we see that this is also why it would be interesting for us to see the developments of the igloo compressor. That in ADR systems, so in drill fridges, normally you run your pre-cooling at full power all the time. In the ADR, as it's a cycle-based cooling, we have the possibility to actually tune down our compressor power regularly, because we don't need all of the cooling power all of the time. So right now, for example, in the L-type rapid, we use 1 watt pulse tube, which eats about 7 kilowatts of energy, which is a lot, of course, but comparable to competing solutions, or even less, because sometimes they use 2 or 3 of them to be faster. So one part of the sustainability is to be fast and thereby require less devices. And the other one is to really actively look at possibilities to reduce the energy intake of the pre-cooling, which is more than 90% of what we actually consume, by intelligently reducing this when we don't need it. And this is definitely possible with our technology, and we're looking into this.
Thank you very much for this answer. And I also see Claudius raised hand.
I wanted to ask if you did the calculation and to what number of qubits, for example, or what number of qubits you think you could host in one of the scale systems?
I think so. The idea is to build it in a way that it is stackable. So we defined modules essentially that give you 20 microwatt of cooling power per module, right? And then you can just stack up as many modules as you like, connect these. So in principle, infinite, but so we would aim at least a few hundred in the first iteration. We also are quite flexible in shielding, so we can build, say, more efficient intermediate temperature stages. So for example, we can add one module that will give us a 200 millikelvin intercept, or we can add a module that will give us a 100 millikelvin intercept at higher cooling power than the 20 microwatt as at base. So this is not yet fixed, but it's of course also something that we would like to align on, especially like you said, to find like a scalable, like a minimum building block to be able to scale this.
Basically, a unit cell of
Yes,
quantum computing
exactly.
host. Yeah, thanks.
Thank you. And I also have one final question from YouTube. So can you explain more on how the characterization automation can be implemented?
So essentially you have your cryostat, right? So and you have a characterization task. So you have a sample that you want to characterize. You can have of these pucks that I showed before. I can show you this. So this is the puck where your experiment sits on, right? You can have many of these pucks. You can make prepare, say, 20 of these and just be ready to characterize all of them. So the only thing you need to do is go there, click it into your cage and transfer it into the cryostat. From there, you have a Python API that will so it's completely controllable. In the end, you send it either you send it you get a measurement option from us that will already have the routines that do this characterization. So you just call these, or you will have your own devices running over wherever. So there's all kinds of things, but we see that our customers normally run it through some IPython notebook in some way where they control their different device stacks. And so the cryostat will always give you feedback when, okay, now I'm loaded, now my temperature is stable, now I have reached this step, so you can freely configure this, and you will always get the feedback that you then can use to create an automated script. If you, of course, buy something from us, this will all be automated already.
Okay, thank you very much for all these insights. Indeed, very, very interesting. So I would now like to move to our last but not least speaker. We have Yiga-chan Uzun, who is the quantum application scientist at Qblocks, and he will round out our discussion with his insights on fully integrated quantum control stack. So there you go. The floor is yours.
Yes. Thank you very much, Mila, and thanks for very nicely pronouncing my name. It's a pretty difficult name, but you did it. You did a great job. Thank you.
I'm glad.
Yeah. So thanks a lot. So yeah, as you said, I'm one of the quantum application scientists at Qblocks. So I will try to first introduce Qblocks, or maybe remind people who already heard about us before. But Qblocks is also based in Delft. And so we are part of a large quantum ecosystem. We are collaborating quite closely with many other partners in the ecosystem, which is pretty nice actually to work in such an environment. So we are already more than 150 people and developing and providing this technology globally. One of the important things for us is to collaborate closely with other quantum companies and also industry academic labs. So therefore, we have many partners and collaborators. Most of these companies are already well known to many of you. So we're also taking parts in European projects. One example is Quantum Internet Alliance. And as mentioned, we are also in the quantum ecosystem in Quantum Delta NL. And we also have two excellent centers. One is QTech, and the other one is Chalmers University of Technology. In these universities, institutes, our electronics or our products are widely used. This actually helps us a lot to make sure that our product is meeting with the expectation of the fields in the big picture. So then we actually, these are critical institutes, really important institutes in these in quantum applications, quantum research. So it helps us to keep always us updated and in the level which actually meets the requirements of the field. So let's try to understand what we are doing as Qublox. So Qublox control stack has actually a central role in the quantum computer picture. What we do, what Qublox control stacks actually does, is actually translates user-defined commands such as quantum gates into electric signals. And these electric signals is actually let us to communicate with the quantum chip. And this is actually back and forth communication, right? So you send your electric signal quantum chip, and then you change the state of the qubit or whatever the device element that you have, and then you get the result of this process operation. And then actually you can define certain tasks on the hardware, the control stack, which can also do a lot of processing on the board. This actually helps us to save quite a lot of time. So you can really minimize quite a lot of experimental overhead by giving tasks to the hardware so that that hardware can actually run all these operations, and therefore without the need of back and forth communication with the user, you can just leave all the operations between the control stack and the quantum chip. So therefore you can really run even complex quantum algorithms on complex quantum chips. And the idea behind the design of our system, our electronics, is actually overlapping, actually in line with the field, how field is evolving. So we all would like to enable functional quantum computer, right? And then this mission is twofold. So on one side, we need to scale up the system. So then we need to reach to millions of qubits. And together with that, we also need to find a way to reduce the number of error rates. So you operate your quantum chip, and there will be a certain number of errors. You need to find a way to actually tolerate these errors so that you can still get the some significant information out of this quantum operations. So at the moment, we are dealing with the hundreds of qubits. So definitely you need the hardware, and all the other previous speakers also mentioned in their technology. Somehow we all try to find a way in our technology which could be scalable. So then this is also one of the idea that we put into our architecture of our hardware. So to understand Qublox technology a bit better, so we have the three important things that we are actually focusing a lot. So one of the important thing is that establishes the first pillar is the excellent analog signals. So we are dealing with the qubits, and to reach high fidelities, we definitely need to generate perfect signals, right? that requires an analog excellence. So this is our highest priority in our product development. So we ensure that the signals that is coming out of our electronics is actually what you wanted to generate. Another thing that this is not only an electronics that generates control signals, but it is actually optimized fully for qubit applications. So every part of the technology is ready to use in your specific qubit experiment. And the final part is that the complete technology is future-proof. What I mean by that is, so we developed something for today which is fully applicable for future requirements. Yeah, so we have been saying since the beginning of the session that we need to scale up. And yes, so at some point we need to scale up even further. And the technology, the idea of our technology and the design is ready for scalability. So this is a very nice illustration actually showing our product. So the cluster. So this, as you see, is a very modular system and highly scalable. So we have the different modules, which I will also try to highlight a bit more in the coming slides. And depending on the different experiments, different applications, qubit applications, then the system can easily be configured. So the user is never dependent on or like limited to fixed configuration, but depending on the needs, then this can always be configured. So that's what we see here for spin qubits, superconducting qubits, or optically addressable qubits. System can be configured accordingly, and then can even be changed in the later stages. So let's try to understand a bit more how we can actually configure this hardware with all the modules that we have. So we have three sections, three class of modules. One you can see on the left-hand side are the DC sources. In the middle, you see analog signal generators, and we also have digital module. So we are covering actually quite a wide frequency range, all the way from DC up to 18.5 gigahertz. And this we do both on the control side. What I mean by control is signal generation. So you output the signals, and we also do the acquisition. So we do readouts, or we have input channels where you can actually measure what would happen with the. Actually, this could be considered as a state readout of your qubit after your manipulation. But within all these modules, I would like to highlight our two new modules. One is QRC. This is our new qubit readout and control module, which actually combines two functionality in one. And also this is built for scalability. So as you see, this has a high channel density, so which provides 6 analog output channels and 2 analog input channels, together with the 12 sequencers, which enables you to do up to 12-tone multiplexed operations, both on the control and readout side. So the frequency range is actually also quite wide. It's all the way from 100 megahertz up to 10 gigahertz, and it has a lot of interesting features because it comes with the RF SOC technology, and this is completely calibration-free module, and this microwave chain actually combines both direct digital synthesis and a single mixer. So you have a channel combine mode, which enables certain the expansion of certain features to even larger values. Another module that we have is on different application domain, as I mentioned on the digital side, that is qubit time tag module, and this is highly used in optically addressable qubits, where you have color centers, NV centers. So there you don't want to only do the photon counting, but you would also like to do time tagging of every photon that arrives to your detector. And this product is actually has very high resolution with the 20 picosecond, which is actually brings a high resolution control of your experiment. So I would like to bring you a bit deeper into our product to give you more feeling what are the capabilities. So this is a nice illustration, shows like a cluster in the sense, then every module is also represented here. And as you see here, we have every module equipped with Q1 core. This is the core of our technology, and every module has number of Q1 cores. And so this is also our sequence processor. So in this architecture, every module is actually, the communication of every module is ensured with two proprietary protocols that we developed. One is sync, which ensures absolute synchronization between every core, every sequence processor. So you can also consider this as an every output and input channels, so then they actually fully synchronize it for deterministic operations. And we also have link protocol, which ensures feedback operations. So within the cluster, this the analog signal that comes into the module is actually processed on the boards, and depending on the outcome of the operation, then the next output signal can be generated from one of the output ports throughout the cluster. So these operations is actually ensured by link protocol. And so this illustration shows the Q1 sequence processor, which actually allows us to do fully parameterized operations. And with that, we can generate various waveforms and pulse shapes, and that actually enables us to really cover wide range of application requirements. So one of the important things that I would like to highlight here, that we can do 1 nanosecond time grid operations, which means that the granularity of the waveforms, the pulses that you generate, is down to 1 nanosecond. And we also ensure that we can, even you want to do such modulated waveform generations, that you can actually, after updating the parameters of each waveform, you can still generate them in your sequence fully gaplessly. So they can really be back to back. These are some of the unique features of our Q1 sequence processors. So on the acquisition side, it works in the same way, but then the tasks are defined differently. There, for the data processing on the boards, you can either do full scope mode acquisition, so that you collect the complete chunk of data and then do your post data processing by yourself, or you can define the tasks on the board as is averaging, thresholding, or any kind of things that you want to do depending on your experimental needs, and the data can be fully analyzed and fitted, and then you can get complete and the finalized result of your experiment. Now I would like to show you how we can actually configure our electronics in certain applications. So in the superconducting qubits, so we are now looking into a picture for 5 transmon qubits. Although we have been saying that we would like to reach to hundreds of qubits maybe, but you still see in the many research labs and also industrial labs, their focus is on maybe a certain number of qubits. But in our scalable cluster architecture, even like on the 5 transmon qubits, we can use one QRC module, which will be completely enough for more than enough actually for controlling and reading out this 5 transmon qubits. And then we will have 2 QCM modules to flux tuning these qubits. And as you see here, only like maybe quite a small portion of the entire cluster is used for 5 transmon qubits here. And if you fill this entire cluster, you can easily reach to tens of transmon qubits control and readout capabilities. So another application example would be on the semiconductors based spin qubits. So now we are looking at a picture of 5 quantum dots where you have 3 quantum dots as our qubits, and then we have another 2 sensor dots for charge sensing, and then we have a microstrip line in the middle for EDSR. So of course the experiment here is a bit different. Then we need to use also D5A. D5A is our silent DC source, which can actually operate for a long time at a very low noise and a very low drift. So it is completely isolated from the ground loops and other interference. So this can actually easily define the quantum dots by applying potentials, and then the QCM module will be coupled to each lines, and then will generate fast pulses for tuning the gates. And then we will also have for microwave manipulation, we will have QRC or QCMRF. And again, depending on the frequency requirement of our resonator, then we can use either QRC and QRM for qubit readouts. And again, as you see here, this system still looks very scalable. By using only these few modules, we can experiment with 3 quantum dots, and we can easily scale this up within a single cluster. And if experiment needs multiple the space of more than the space of the single cluster, then you can easily get your other modules in another cluster mainframe, and you can daisy chain and then use your complete synchronization and link protocols. So the same experimental example can be made with the color centers. So here we are talking about the color centers in the diamond. So we have 3 qubits, and these 3 qubits can be microwave controlled either with QRC or QCMRF, as I said in the other example. And now we have a QTM module, which is actually coupled to single photon detectors, where we can do the readouts of the photons that arrives to detector. We can do either photon counting and the time tagging all together. And the other optical elements like acousto-optical modulators can be driven with the QCM module that we have, which acts as an AWG here to modulate at certain frequencies. So, but then how are we going to run all these experiments, right? So we need a certain way of communicating with the hardware, and that is about this. That brings us to software. So in Qblocks, we are evaluating the software in 2 abstraction level. One is low and a high level. In the low level, we are using assembly language, which is enriched with the Q-codes parameters. So the assembly language is actually accessible by the users. And in case users require certain customization and more flexibility, extensive access to the hardware, then this is actually pretty useful for users to have this function available. So this allows users to generate even like very customized experimental operations. But our aim is to actually standardize our high-level software, which is Quantify. We are developing Quantify together with our collaborator, Orange Quantum System. They are also part of the ecosystems in Delft. So we're developing this together, and what we are aiming is actually what we're providing is more like gate level operations, so that the certain quantum gates and then operations are already available in the libraries. User can reach to these libraries and then define the quantum circuit by themselves, and then this can be translated into certain pulse visualization, and experiments can easily be run. So this is more like ease of use and more intuitive experimenting of the qubits. At the very beginning of my talk, I was trying to highlight 3 pillars, which is highly critical for Q-blocks. And the first one was the analog excellence. And in this slide, I wanted to show you the proof of these 3 pillars. And the first one, for the analog excellence, I would like to show the ultra low 1/f noise of our QCM module. So we actually compared our module output specs with certain alternatives on the market that are available, and this is one of the key results which ensures that we are providing extremely low 1/f noise performance here. And together with that, our QCM module is also outputting at the high dynamic range, which gives a bit of room for users to suppress the noise even further, if needed, of course. So in addition to that, we also characterize the phase stability of our modules, and we show that even for like extended period of use, the stability is guaranteed on our output signals of the modules. The second one was the readiness of our modules and product in general for certain qubit applications. And here we experimented a quantum error correction with one of our users, and we demonstrated surface 17 experiment using our electronics, and we showed pretty reliable operations and performance in this experiment. And of course, such an application can be extended to many other experimental cases and application cases. And then if there is an interest within the field and or the users, so we are always happy to chat about that and then perform certain experiments together. Finally, the third pillar was the future proof. So the design actually already shows the scalability of the system. So and this animation on the right hand side nicely shows actually how we can reach to 1,000 qubits. So that is of course just an animation, but completely doable with our electronics, with our architecture at the moment. Before closing, I would like to highlight once again a few important things which I try to touch throughout my talk. The first thing is that we are trying to minimize the overhead. So we try to enable fast operation with high precision. So both on the control and readout side. So this is highly important for us, and we do this thanks to our excellent analog performance in our modules. And what is also very important, of course, we need to implement the feedback operations, right? And this also needs to be quite fast. And that is also one of the things that we pay attention. And after all these features are combined, then you can show that your system it can easily be scaled up to the requirements of the quantum computing field in general, which is accelerating towards hopefully thousands of qubits in the near future. Thank you very much, and I'm happy to hear if there are any questions.
Thank you very much, Hugo-chan, for this informative presentation on the topic of quantum control stack. There is one question on, one question on YouTube. So, is the Python software stack open source, or are there any other sources?
Yeah, so it is open source. So users or like interested people can reach to the software.
Perfect. Thank you. And does anyone here have any further questions? Yeah, I see Haysam.
Maybe I have one question. Yeah, thanks again also from my side for the talk. So you mentioned, I think in the title, that this solution is, let's say, fully integrated solution. So how, I mean, what would you say are the advantages compared to maybe some kind of a hybrid or modular solution? So what is the big advantage that you're having here?
All right. Yeah. So if you look into the hardware, so maybe let me get to this one. Maybe this is a nice illustration to talk about that. So they're fully integrated, right? So then you don't want to. So in your quantum experiment, you don't want to do only control experiments. So you want to generate your signals, and then you do the acquisition, you receive signal, and you do some operations with that, some onboard processing, and then you want to generate your next pulse, right? So it's kind of a closed loop that it's like a back and forth operation. So what we do here, we integrate all these functionalities in the single cluster mainframe by having different type of modules. So this definitely adds and helps on the time of this operation, right? So then you minimize the overhead extensively. And because the system is also modular, because you want me to compare the other modular solutions, because our system is also highly modular. So that's what I also wanted to highlight. So depending on the requirements of the experiment, the system can actually be configured, right? So then you can have different type of modules for every experimental needs, operational needs. So for the readouts, for the microwave, for baseband control, and everything can be embedded in the single cluster mainframe. And this complete experiment for which qubit requires can be done in complete synchronization. So I think this is key here. So you need to synchronize, make sure that everything is synchronized, right? So you don't need to deal with the external clocks, or like that you need to align timing and everything, which is completely avoided here. So you don't need to do that, because all the complete communication is taken care by the cluster mainframe. I hope that explains or answers your question.
Yeah, thank you very much.
Mm-hmm.
Thank you. And I also see a hand raised by Clemens.
Right. So thank you for that very nice talk. There was a point on one of your products that it's calibration free. What does that imply?
So this is a QRC. So normally in some high frequency modules, or like high frequency instruments, so you are up converting your signal using IQ mixers and then local oscillators. They are on the board, actually. This is in the signal generation path. And these IQ mixers, and that needs to be calibrated. And so there could be some leakage on the signal that comes from local oscillator, and that leakage should be suppressed. And this is due to the components that you're using in your up conversion, or in your high frequency signal generation chain. And in this particular module, we are not using this. So therefore, the technology here is completely different. And here we have we are combining two technology. One is the direct digital synthesis, which avoids any analog component, and the other one is a single mixer. And that technology is actually enables to generate the signals up to 10 gigahertz without the need of any calibration.
Great. Thank you. Let me quickly check. I don't see any further questions, neither on YouTube nor in here. Does anyone have any final questions? Nope. So thank you, Yagichan, very much once again for this very insightful presentation. And yeah, I would say that brings us to the very end of today's quantum leadership session. I would like to extend a big thank you to all of our distinguished speakers for sharing their quantum expertise with us today on the topic of control electronics and cryogenics, and surely to all participants for joining us live. I would like to also remind you that this session is being live streamed on YouTube, and the recording will be available on our YouTube channel shortly after the event. So if you haven't already, please like the video, subscribe to our channel, and follow us on social media to stay updated on all future events. And once again, thank you all for being part of this important discussion. Stay tuned for more updates, and we hope to see you very soon at our upcoming sessions outlined earlier in the presentation. With that, I wish everyone really a wonderful afternoon.
Thank you.
Thank you.
Bye.
Thank you.
Bye.
Hey.
Bye-bye.
Goodbye.
Goodbye.